Okay, so ladies and gentlemen, we are going to look at the concept of thermodynamic system and thermodynamic surrounding. So thermodynamic system is also the something as you can just also call it as a system. So thermodynamic system is the something as system. You can just call it system. So what is a system? A system is a region or a space where processes are taking place. Assuming now you have a cup. If you have a cup like this, if you take this as a system, if you take this as a system, it means that anything outside this is considered as a surrounding. So system is depend on what you consider to be your system. Like for example, you can take the whole of this conical plaques. You can take the whole of these conical plaques as a system. So if you consider this conical plaques as a system, it means that anything outside the conical plaques is considered as a surrounding. If you consider your room as a system, it means that anything outside your room is considered as a surrounding. So it means that in a system, usually there is a boundary. So if you consider this place as your system, if you consider this place as your system, then this is your boundary. This is your boundary. And anything outside this system is considered as a surrounding, is considered as a surrounding. So we have thermodynamic system and thermodynamic surrounding. So a system is considered as a region where processes are taking place, and it depends on what you consider, on what you consider as your system. So for example now, as we have different types of system, as we started discussing. Number one, we have an open system. So an open system is a region where both matter and energy can be exchanged between the open system and the surrounding. Like for example now, if we consider, let's say this is our system. So if this system allow the exchange of matter and energy, this is our system. So if this system allow the exchange of matter and energy, the exchange of matter and energy between the system and the surrounding, so that types of system is considered as an open system. It's like you have a room, and between your room, if you consider your room as a system, so it means that between your room and outside your room there is an exchange of matter and energy. So if that is what actually happened, then your room is considered as an open system. It's considered as an open system. So water in an open system container, so if there is an exchange of mass and heat with the surrounding, then that type of system is called or is considered as an open system. So a mass can be an object or can be matter. So if there is an exchange of heat, if there is an exchange of heat and mass between the system and the surrounding, so that type of system is considered as an open system. Ladies and gentlemen, let me tell you, even the earth itself is operating under an open system because there is an exchange of mass and energy, and that is why we are even living on the earth. That is why we are living on the earth, because it is operating under an open system. And then also the next type of system is a closed system. So what is a closed system? A closed system is a system where there is only transfer of energy but no transfer of mass. So it means that it's only energy that can be transferred between your system and the surroundings. So if you have such kind of system is considered as a closed system, it means that, like for example, let's say you have your container like this. If you have your container like this, and let's say the container only allow the movement of carbon dioxide it doesn't allow the movement of carbon dioxide between between the system and the surrounding, but it means that it doesn't allow the movement of carbon dioxide in and between the system and the surrounding, but it allow the exchange of energy. It allow the exchange of energy between the system, but no exchange of carbon dioxide or any form of matter or any form of mass. It means that that system is considered as a closed system. Then the last one is an isolated system. So what is an isolated system? So an isolated system is a system where there is no mass transfer, no energy transfer. It means that nothing is getting in and out, or nothing is exchanging between the system and the surrounding. So that type of system is considered as an isolated system. So then the next thing that we are going to look at is exchanging energy. So according to the first law of thermodynamics, according to the first law of thermodynamics, first law of thermodynamics, the law states that energy can neither be created nor destroyed. So energy can be exchanged between objects. So energy can neither be created nor destroyed, but it can be exchanged from an object, and it can change a form from one form to another. Like for example, we consider sun as our primary source of energy. So sun is our primary source of energy. So if you consider sun as a primary source of energy, and the energy that is present in a sun is solar energy. So when plants generally absorb this solar energy, when plant generally absorb this solar energy, then it converts the solar energy plus smaller molecules to generate a complex compound. And this complex compound is usually the types of foods that we are taking. Complex compound, when you said complex compounds, it comprises something like starch, and the form of energy and the energy that's stored in a starch is chemical energy. So the storage form of energy is chemical energy. And of course, when we consume this starch, it will convert this chemical energy into mechanical energy. So it means that from solar energy is converted into chemical energy, and then from chemical energy then is now converted into mechanical energy. So also at the same time, this chemical energy in some other organisms can change into light energy. Like for example in fireflies. So it means that energy can neither be created nor destroyed, but it can change from one form to another. So this is what you call a first law of thermodynamics. And then now you see, so energy can also be transformed from one form to another. So you see at the same time, energy can be converted from heat energy can be converted into light energy, and light energy can be converted into sound energy. So you can never create energy and you can never destroy it. That is according to the first law of thermodynamics. So there is a likelihood that energy can be transformed from one form to another. So that is what you call energy exchange. So this is, of course, the first law of thermodynamics. That is what I explained earlier. or we call it the law of conservation of energy. So when energy is exchanged between object or transformed into another form, so all energy is still there. So the total amount of energy in the universe before the change has to be equal to the total amount of energy of universe after. So it means that the total amount of energy in the universe is constant. Is constant. Is neither change. So if you produce any amount of energy, if the universe is having so amount of energy, so that amount of energy will still remain constant. It will never be created. It will not be destroyed. Rather, it will actually be changing from one form to another. So these types of this process is actually considered as a law of thermodynamics or law of conservation of energy. So, and then the next thing that we are going to look at, ladies and gentlemen, is internal energy. So, what is internal energy? So, the amount of when, for example, the internal energy is a total amount of kinetic energy and potential energy a system possesses. So, if you have a system, so when you add the summation of kinetic energy and the potential energy of that system is considered as an internal energy. Let's say, for example, you have your beaker, or you have your conical plugs like this. So the sum of the kinetic energy, the summation of the kinetic energy and the potential energy in this system, if you add them, if you sum them together, that is what we call internal energy. So internal kinetic energy plus the potential energy of a system is what we call internal energy. So the change in internal energy of a system depends only on the amount of energy in the system at the beginning and end. It doesn't consider what happened in between. So that is why internal energy is considered as a state function. As a what? State function. So a state function is a mathematical function whose result depend only on the initial and the final condition, not on the process used. Assuming now you have a particular condition, so the condition started from A, then changed to B, and then from B to C, and then from C to D, and then finally to Z. So you see, what is the initial state? The initial state is A, and the final state is Z. So a state function is a function that depends only on the initial and the final state. It doesn't actually consider what happened in between. That is state function. And there is also, apart from a state function, there is also what you call path function. So you should understand what is the difference between state function and path function. State function is a function that depends only on the initial and the final states, but the path function depends on what happened in between. Like, for example, between it started from A and finally to Z. So a path function is actually concerned with what happened in between A and Z, but state function is just only about A to Z. Like, for example, assuming now you travel from Zaria to Lagos. But before you go to Lagos, you have to go to Kaduna. From Kaduna, you have to pass Kogi State, you have to pass through Osun State, Ibadan, then you finally go to Lagos. So a set function only depends on your starting point and the final points. Your starting point and the final point. So that is a state function. So apart from internal energy is a state function. So apart from that, we also have other state function. Even enthalpy is another example of state function. Entropy is also another example of state function. So internal energy is actually internal energy and enthalpy as well as entropy are typical example of state function. So that is why, for example, you can have an integral of T1, T naught, delta H, delta H dt, that is differential of delta H. Finally, you just have enthalpy of products at time 1 minus enthalpy of reactant at T naught. So it just only started with final and the initial. So enthalpy of the final minus the enthalpy of the initial. So that is why if you look at the internal energy itself, the internal energy is equal to the internal energy of final minus the internal energy of initial. So if you look at the chemical reaction, generally in a chemical reaction, there is what you call a reaction mechanisms. For example, if you now have A plus B to produce C and D, so before A and B convert to produce C and D, there are so many steps. There are so many mechanisms. There is so many steps that are involved before you finally have your C and D. So in the state functions, we are just after the initial reactant and then the final product. So that is why in our internal energy is equal to internal energy of the product minus internal energy of the reactant. You can take it as that, or you can now say the internal energy of final minus the internal energy of initial. So I think at this point, ladies and gentlemen, we were able to understand number one, we have internal energy, and internal energy is the sum of energy, is the sum amount, or is a total amount of kinetic energy and potential energy. So the total amount of kinetic energy and the potential energy that are found in a particular system, that is what we call internal energy. And this internal energy, it actually a state function, is an example of state function. And a state function is a function that depends only on the initial and the final condition. It doesn't concern of what happened in between. And then apart from this, we have also another examples of the state function, which is enthalpy and entropy. And also apart from state function, we have a path function. A path function is a function that depends on what happened in between. It's not actually, it doesn't concern about the initial and the final product. What it's after is actually what happened before the final. Okay. So now, what is a state function? So a state functions are the properties that are determined by the state of system, regardless of what conditions was achieved. Assuming now you have a temperature of 37 degrees centigrade. You have a temperature of 37 degrees centigrade. So if you now have a temperature of 37 degrees centigrade and it's now dropped to 25 degrees centigrade. So you see the initial temperature is 37 degrees centigrade, but the final after is actually cooled down is now changed to 25 degrees centigrade. So the start function is just after what is the initial temperature and what is the final. But you know that, of course, before the temperature is dropped to 25 degrees centigrade, it must drop maybe from 27 degrees centigrade to 23 to 24 to, sorry, from before it reaches 25, maybe from 37 to 36 to 35 to 30 to 26 before it finally reaches 25. So you see, a state function is doesn't actually concern what temperature actually drop before it reached to 25 degrees centigrade. What it is after is just the initial and the final. And then another examples of these state functions we also have, apart from the enthalpy, entropy, internal energy, we also have pressure and volume. The pressure, we have pressure, So pressure and volume is also another examples of state function. So there is also temperature. So final and initial temperature, final volume and initial volume, final pressure and initial volume. So you see final and initial final. So all of them are examples or are fall under state function. But for the path function, it depends on what happened in between. So that is actually state functions. Even this one is just trying to actually explain what happened in a state function. That is, you have temperature of 100 degrees centigrade is now dropped to 25 degrees centigrade. It means that there is an internal energy in the system that caused the drop of temperature from 100 to 25. And so also here the temperature is 0 degrees centigrade and is now increased to 25 degrees centigrade. So to calculate the internal energy, so it depends only on the initial internal energy and the final internal energy. So now the next thing is energy diagram. Energy diagram. So in the internal energy diagram also is just only depend on final and the initial. So when energy is added, so delta G, it means that when the final energy is higher than the initial energy, so the internal energy is always positive. So if the final condition has a larger amount of internal energy, that is final condition, that is the final energy, if it is actually larger than that of the initial, then the change in internal energy will be positive. And then if it is initial, if the final condition has a smaller amount of internal energy than the initial condition, then the change in internal energy will be negative. So you should understand this condition. If the final is higher, of course, if it is higher, you subtract the initial, so it will be positive. But if the final is lower than the initial, so when you do your subtraction, it will be negative. So that is that. So now, the next thing is energy flow. So when energy flow out of the system, it must flow into the surrounding. So if you have energy in a system and that energy is actually flowing out or is actually moving toward the direction of the surrounding, so when energy flow out of the system, that's the surrounding. So the change in internal energy of the system is always negative because it's the energy in the system that is reducing. So since it is reducing to the surrounding, then the internal energy will be negative. And of course, when the energy flow into the surrounding, so when energy is actually leaving the system and getting into the surrounding, so it means that the surrounding is gaining heat or is gaining energy. So that is why, because it is gaining, it is going to be positive. So therefore, finally, if you have this condition where there is a release of energy, if you look at it here, you can clearly see that in this case, this is our system. This is our system. Okay. So now, if you can see clearly, if you can see clearly here, this is our system, and there's an energy flow from the system to the surrounding. If you can clearly see from here, you can observe that there is a flow of heat from the system to the surrounding. So it means that the energy or the internal energy of the system is decreasing. So since it is decreasing, so the change in the internal energy of the system is less than zero. So since it is less than zero, so any number less than zero, of course, it is going to be negative. And of course, since the energy, you are enriching the surrounding with the energy because the energy is leaving the system, then of course, our change of internal energy of the surrounding is going to be greater than zero. So that is why it is positive. So Therefore, at the end, we'll have a change in internal energy of the system is negative and the change in the internal energy of the surrounding will be positive. So the first thing that will come into your mind, okay, the system is actually releasing energy, so it's reducing energy, so it will be negative, and the surrounding is earning, is getting, is obtaining the energy, so therefore it will be positive. So what happens now if the energy is flows into the system? That is leaving the surrounding and getting into the system. So if you have such condition, look at it. This is the surrounding. So in this case, the heat is leaving the surrounding and getting into the system. So therefore, this internal energy of the surrounding, or the change in internal energy of the surrounding, because the heat is getting into the system, so therefore is going to be negative for the system, for the surrounding. And then for the system is also going to be greater than 0, which is positive. Okay. So now the next thing that we are going to look at is the energy exchange. So energy is exchanged between the system and the surrounding through the heat and work. So heat is Q. So the quantity of heat is Q, small letter Q, and the work done is W. So change in internal energy is equal to the amount of heat plus amount of the work done. So if you sum this together, then it will give you a change in internal energy. So the change in internal energy is equal to Q plus W. So Q and W are not state functions. So their values depend on the process. So you should understand now that we have heat and W, which is work done. They are example of path function. Path function. Please, you should note this. There are example of path function. So now we have change in internal energy is equal to Q plus W. So we have different condition in which this formula can change. Let's look at it. So Q, that is heat. Q is positive when the system gains heat energy. So it means that if the system is gaining heat energy, then our Q is positive. But if it is the system that is releasing heat energy, if it is the system that is releasing or that is losing heat energy, then our Q is equal to be negative. So it means that in this condition, if you have this, it means that when the system is releasing heat energy, then the change in internal energy will be equals to delta E is equal to minus Q plus W. But if it is the system that is gaining or that is obtaining the heat energy, then the formula would remain like this. And then what of work? If also the system is the one that is gaining energy from the work, so when there is a work done on the system, that is when it's the system that is actually gaining the energy from the work, then the formula is also going to remain like this. But if it is the system that is releasing energy by doing the work, then W is going to be negative. So therefore, the formula in this case for the W, delta E, is equal to Q minus W. It's equal to Q minus W. So now, what if the internal energy or the internal energy is, in the case of, is the system that gets the internal energy that gains. So remember, whenever there is a gain, either in internal energy, either in the energy itself from the work, or internal energy, so they are all going to be positive. But if it is the system that is losing, whether the heat energy, whether the work done, whether the internal energy, then it will now change to negative. So you should always try to understand these differences, because we are going to solve some problem. So once we are coming to solve those problems, then we are now going to see how we are going to interchange those values. If you miss this gap, if you miss this, then you are going to actually have a lot of problem. So always put at the back of your mind, if it is the system that is losing anything, or if it is the system that is losing, whether work, whether heat energy, whether the internal energy, so they are all going to be negative. They are all going to be negative. But if it is the system that is obtaining, or that is gaining, or that is benefiting with something, it means that it is going to be positive. So that is the most important thing that you should understand here, ladies and gentlemen. So now, the energy exchange. So if there is an energy exchange, of course, there may be an energy exchange between the system and the surrounding. It can be a work done or a heat. So energy is exchanged between the system and the surrounding through either heat exchange or work being done. So if it is work done by the system, or work done by the system, there is work done by the system, and there is also work done on the system. So you should understand how the sign interchange. So the next thing we are going to look at is actually exothermic reaction. So exothermic reaction is a reaction in which there is a loss of heat. Heat is absorbed by the system. So if heat is absorbed by the system, remember I told you, if it is the system that is obtaining or that is gaining. So you see, in the case of endothermic reaction, the system is gaining, is absorbing heat. So Q is positive. But if in the case of exothermic process, the system is the one that is releasing, that is evolving, that is giving out the heat. So Q is negative. So in an endothermic reaction, the reaction vessels usually cools, so heat is absorbed. So because the vessels is cools, so it needs to absorb heat. So in this case, energy is added to the system, so Q is positive. And for the exothermic, the reaction vessel is warm, so the heat will be releasing, will be evolved. So therefore, the energy is subtracted from the system, so Q is negative. This is actually some examples of exothermic and endothermic reactions. So you see, a chemical heat packs contain ion fields that are oxidized in an exothermic. So this is just an example of exothermic and endothermic reaction. So now the next thing is actually the pressure volume work. So Phoebe, of course, work have a formula. Remember, even from our basic concept of physics, remember, work done is equal to force times distance. And of course, what is the formula for calculating force? Remember, there is a formula which says pressure is equal to force all over area. So you can make force subject of the formula. So therefore, force can be equal to pressure times area. So you can now just replace the force with PE. So therefore, we have force times area times distance. And of course, force times, area times distance is volume. And that is how work done now change from force times distance to pressure, of course, and volume. So it's now changed from this to pressure and volume. It's now changed to pressure and volume. So you're going to have something like this. So that is why we have work done is equal to pressure times volume, but it can be the change in volume. So therefore, when gases expand,